Thanks very much. Okay, so what I want to talk to you a little bit about today may not, on the face of it, seem very directly related to the resources used in quantum computing, but actually it's fundamentally linked in some way. So what I want to talk to you a little bit about is some work we've been doing on developing tools for programming quantum computers, and then for doing things like automated resource estimation to tell how many gates, how many operations of different kinds are being used. And fundamentally what we've been doing is to try to build a chain that goes from classical code, from code you could run on a conventional computer, to code you could run on a quantum computer with some acceleration. And this gives a very straightforward like-for-like comparison. So you're comparing classical code to the exact same functionality implemented in a different, hopefully more efficient way. Okay, so as I see it, there are basically two barriers to getting to useful quantum computing. The first barrier is that we need better quantum computers. If we don't have lower noise systems, if we're stuck with the systems we are, it's going to be very, very challenging to get useful work out of them. The other problem we have is that we need to harness whatever systems we have to try to do useful work. And that's not really a hardware problem, that's a software problem for the most part. So we're now kind of entering this interesting regime where both progress on hardware and progress on algorithms, for example, can lead to, potentially useful applications for quantum computing. So the field is, I guess, in a place where it can potentially reach advantage in two different ways, either by figuring out how to better use the systems that are just emerging now, or by getting to fault tolerant systems, getting to a very low noise regime. For us, our focus is on algorithms for that kind of fault tolerant regime. So as you get past noisy systems, as we start to get true error correction, what kinds of algorithms are there? How can we get to a point where we can use quantum computers for useful work? Because the reality is, even if we had 1 million error-corrected qubits tomorrow, using them to do useful work, okay, we could factor large numbers. There's a bunch of things we know how to do, but there's a lot of things we don't know how to do. So how do we get to a situation where we can use them for a broader range of tasks? Okay. So what we've been focusing on is to try to build a system to go all the way from classical code, so this being code written in, say, MATLAB or C or C++ or something like this, that can run on a conventional computer. Can we automatically generate a quantum algorithm from this that we can then compile down and execute on hardware, run it, get results back, return it to the user? And that hardware may not be today's hardware, but it may be future hardware, right? So the question is just, for us, can we build a system that can go from classical code all the way down to something that can do all of that mapping required to execute on hardware and back up? So we've been doing that, and I'm going to tell you a little bit about our work on this, about 3 different levels of programming that we've been focusing on. So the first is what we call Hydrogen, so this is our low-level programming language. And basically what this is intended to do is to specify individual operations that a quantum computer should perform. So this can be thought of either at the gate level, or you can think of it as pulses or similar. Most of what you're going to see is described as gates. So in general, you can see on the right-hand side of the screen, you can see a sample of this Hydrogen code. Looks pretty much like any other gate-level programming language. So we have qubits at the start being assigned to variables A and B. We have a Hadamard applied to qubit A, a C0 applied to qubit A and B, and so on. So this does not look very different than many of the other programming systems that are out there. But the difference comes that our compiler does not know what any of these operations are a priori. Instead, what we're doing is we're doing gate synthesis. We're reading in a description of what the operations do. So we call them language files, but basically you can think of it as this code in the center of the screen, where we're defining the individual operations in terms of their effect on the logical Hilbert space of the system. So we're specifying them either by a set of Krauss operators or by a set of POVM elements. And we can use this to generally describe pretty much any kind of operation that could happen within a system that satisfies a kind of Markovian assumption. The idea then is that with these in place, with the descriptions in place, you can define whatever kinds of operations you may want to use. You can use them within our programming language then. So if I want to add in a square root swap gate, if I want to add in an XXZ, an XXZ coupling or something like this, I can just add it straight in by using this framework to describe whatever operations I want, and then the system will synthesize them to whatever operations the system can do, just using kind of standard gate synthesis techniques or using Solovay-Kitaev if you have a discrete gate set and so on. However, most of the existing programming frameworks are kind of limited. And one major limitation comes from the fact that they are almost all designed to implement circuits or something very close to circuits. And the problem with this is that if you think about what we're trying to do, we want to go from purely classical code, compile it all the way down to run on quantum hardware. One immediate problem you run into is the halting problem. So you need a way, while loops exist in classical programs, and you can't unroll them necessarily to a circuit. So we need a way to be able to implement quantum programs that have indefinite runtime. So we need to be able to describe these within our gate level programming language. And the way we do this is by introducing basically control flow blocks that you can think of as representing you can think of them as representing bits of code that are going to be executed. And then based on a particular condition, the program's going to branch to one of several possible following blocks. And we just keep going through it, stepping through it that way, just in a kind of flow diagram. So the way we formulate these blocks is along with the kind of gate level code, we have a header for a block. All of our programs start with at start. We have a list of successor blocks, and then we have an instruction that says how we're going to proceed to the next block. And it turns out if you have this, you can implement a Turing complete language. You can run, you can directly simulate an arbitrary quantum Turing machine. This is kind of useful because then it gives you ways to incorporate things like loops that you would not otherwise be able to do, or at least while loops, loops that you can't unroll. When we put these together, there's a question then of how do you execute this? Because it's one thing to be able to express it, but it's another thing to actually run it on hardware, and lots of the hardware that's available at the moment, at least commercially, is not adaptable. It's not able to do adaptive flow control. So you have a measurement that occurs within the body of a circuit. You can't do anything about it until after the circuit is completed. In that case, it turns out we're able to compile these to a kind of hybrid classical quantum computation, where what we do is we execute the circuit until we hit some unknown value. We take the measurement results we've seen up to that point, and we use that to unroll the circuit further. And then we execute that larger circuit and post-select on seeing the results we got from the first round. And then we use that second round of measurements together with the first round of measurements to unroll even further. So we go back and forth in this kind of hybrid way with post-selection, and we can essentially implement any arbitrary time computation. So even if it has indefinite runtime, we're able to essentially directly simulate a Turing machine. So this is nice because it gives you things that you can run, programs that you can run that are not circuits. The other advantage of doing this kind of structure is that it's pretty naturally set up for being able to implement on something like an FPGA, so that if you have a system that can do the fast feed-forward logic, then it becomes easier to target that kind of system. The next level up from this we call Helium, and this is the one that we actually expect people to program more in. And this is basically like BASIC. So it has exactly the same flow control as BASIC and exactly the same gate level operations as hydrogen. So we have if statements. They can be controlled on classical values or they can be controlled on qubits. So in this case on line 5, I say if A, and A is in square brackets, which means if qubit A. So what this whole thing means is that I should make a controlled version of the C0 gate. So the compiler is going to turn this into something that's equivalent to a Toffoli gate. The next thing I have down there is a repeat until loop, and this is our analog of a while loop. So it lets you do things that have indefinite runtime. So this is going to just this is going to keep calling the subroutine entangle, which is defined below, until a particular value is seen. So that can be conditioned on a measurement value, for example. And what's kind of nice with this, I mentioned using the post-selection to unroll earlier, but it turns out because of the principle of deferred measurement, you can push all the measurements to the end, make everything unitary, and the only measurement you're ever doing then becomes the has the program halted yet measurement. So you're just measuring one qubit that says, has the Turing machine halted yet? And for that, the overhead of the post-selection is at most linear. So you don't have any exponential blow up because there's a bunch of post-selections. Instead, you just have at most linear overhead, even if you're running on hardware that can't do this kind of adaptive flow control. But what's kind of neat is just going beyond this kind of basic level programming language, we can also do things like include these C2Q files. So we can include subroutines that are written in different ways. So in this case, when I say include .c2q, what I'm doing is I'm going to generate a subroutine from a file that's written in C, just in plain C. There's a couple of restrictions because it's going to generate a circuit fragment. So the restrictions are that I don't use while loops, that I don't do any OS calls, or else I'm going to have to compile the entire OS along with the subroutine. And that I don't do anything crazy with pointers like trying to access a region of memory that's not defined, because then the code has undefined behavior. But if we avoid these things, then I can say the file I want to call. I can say the mode I want to operate in. So I can say default if I just want a Toffoli circuit. But if I know I'm going to use this within Grover's algorithm, for example, I can say I want to use this as an oracle, which means that I only need to compute it up to phase. If the phases are wrong, no problem, because they're just going to be uncomputed the other side, and they're going to commute with all the control operations I do off them. We also have load TDAP mode and so on. But each of these saves resources. So if I know it's going to be used in Grover's algorithm, I get a 3/7 saving on the number of T-gates and so on. We can also decide how aggressive we want to be about reusing qubits. There's trade-offs here. If you say you want to reuse qubits, there are less qubits used, but the circuit depth increases. If we want to do all of the linear operations in place, we can. We save qubits, but it comes at the cost of deeper circuits, and so on. So this is just a comparison of some results, our compiler versus some results that have appeared in the research literature. So in particular, this comes in relation to a paper some of you may have seen from the group in Goldman Sachs that were looking at resource counts for quantum Monte Carlo for options pricing. And they found that, with those circuits, the bottleneck they were getting was just a classical subroutine. So it's just where they're computing e to the minus x, but they need to do it coherently. They need to do it as a subroutine within a quantum program. So they had been using some results from the paper 1 here that came out in 2018. And this was, had explicit circuits for inverse exponential. There was a subsequent follow-up paper that showed that you could reduce these costs a little bit in 2021, and our numbers are from December 2021. So what we did was just compared the compiling this e to the minus x for either 21-bit or 32-bit precision for x in the range 0 to 10 or x in the range 0 to 100. And I guess what you can see why, in particular, the Goldman Sachs paper was seeing these subroutines as being extremely expensive is because if you use this first option, it takes about 15,500 T-gates. 15,500 Toffoli gates to implement e to the minus x. Follow-up paper reduces that significantly, but I guess you can see going through our compiler, this is about 15 lines of C code. There is no manual intervention. This is not people constructing quantum circuits, knowing what they're doing. This is an automated system doing it directly from C that you could run on your computer. And we're getting pretty large improvements. So I guess you can see the difference between 15,500 and 140 is a factor of about 112. So we're getting really large reductions in the number of gates used. And part of the reason for this is because if you try to solve these problems by hand, you start seeing simplifications that have patterns in them. But if you turn this into a giant SAT instance and you just try to numerically solve it, you pick up a whole load of stuff there's no obvious pattern to. So you can really boil things down quite a lot more in many circumstances. And I guess you can see that in every single case we have quite a large improvement, not just over the original implementation, but even over the improved implementation. I just wanted to show you this kind of example of some of the trade-offs you have to show you that there's no one best option. So these numbers are for computing a dot product. So we have 2 vectors with 3 entries in each, and we're just computing the dot product of each. And these are the different numbers of gates that are used, different numbers of qubits that are used, different numbers of H, T, T dagger, C naught, along with their T depth. And depending on the different options that we use through the compiler, because we're using different constructions for each one, there is no best one for any particular, kind of in an overall sense. If I measure which one uses the fewest qubits, I get a different answer to which one has the lowest T depth. If I say which one uses the fewest C naught gates or fewest T gates, whatever, I'm going to get different answers for each. So there's no right choice. It depends what you're trying to accomplish. I wanted to show you, just to finish off, what I talked about a little bit about going from classical code to quantum algorithms. So if you think of some code written in MATLAB, for example, we're going to try to accelerate that. And the way we do this is by tackling 2 different sources of complexity in the program. So the first is, let's call it explicit complexity, but what I mean by this is that it's from the control flow that the programmer has written into the program. So they've written nested for loops, they've done different things like this, they've recursive subroutines, and those are causing the dominant complexity of the program. The other part is coming from kind of implicit complexity where, depending on the programming language, maybe you call some function, but that function does an enormous amount of work that depends on the size of the input it was called. So maybe you're calling the determinant function in MATLAB or something like that, where it's, kind of big O of n cubed or something. It's very unlikely to be the case that it's just the number of instructions we have, that it's just the length of our source file. If that's the case, we can't do anything for you. So if you have 10 lines of code and it takes 10 instructions, then none of these techniques are going to work at all. There won't be any speed up. However, I want to show you this kind of in action. This is real output from the compiler, but it's just drawn up on the PowerPoint, so it's kind of easier to see what's going on. What this is it's a MATLAB subroutine. Well, it's a MATLAB function called recursive search. It takes in a function handle f, and what it's going to do is it's going to try and find the global minima for f. So it's just an optimization function. The way it does this is it expands a grid across the input space for f. It samples that grid, finds the lowest point in that grid, and then expands a finer grained grid around that point, samples around that, and just keeps recursing down. So this is guaranteed to find the global minima for f if f is bandwidth limited, and if you pick your grid to be fine-grained enough that it's that the separation between grid points is less than the bandwidth. Okay, so the first thing that happens is that the system replaces intermediate variables like lattice points. Then it eliminates them. Then what it's going to try and do is it's going to split apart the loop. So it's going to take this inner for loop and try to pull it apart. It gets separated, fissioned into 3 different for loops. Again, same thing as before, the intermediate variables are substituted and eliminated. The empty flow control is eliminated. Now this internal loop here, it turns out it has a very particular structure. In particular, what it's doing is it's defining the dth element of some array or some vector, and that dth element does not depend on d minus 1 or any other values of d. So we can replace this with a particular function that's saying what that loop was doing. It's saying just let's do a column matrix definition according to this function here. And this extra bit of flow control, the if, is just to catch what happens to d so that there are no side effects. There's no change in side effects. Because the value of d on exiting this loop, if dim is 0 or less than 1, it's going to be 1. And if dim is greater than 1, d is going to be equal to dim. So that's what this extra flow control is appearing here for. These intermediate variables then get eliminated again. The empty flow control gets eliminated again. I guess you can see that this is kind of a regular process that's happening again and again and again. So now what's happening is this, this variable x is getting substituted for, but because x is a function of the loop index m, instead of just replacing it directly, it's getting replaced with a function. So we're just breaking it out as a separate function and replacing with a call to that function. Next thing that happens is we're now at a point where we can fission this outer loop. So this gets split into 2. Again, the first one has a particular form. So in this case, I guess what you can see is that x gets overwritten every iteration of the loop. So the only thing that matters is the last iteration of the loop. So the loop can be eliminated. Now, we get to the same point. Is x used again anywhere? No, it's not. So that's an intermediate variable that gets eliminated. And now we're at this final loop. So in this case, this loop has a very particular form. It's a for loop, and the only thing inside this for loop is an if statement. So what we're going to have is we're going to have an iteration, and most iterations of the loop, nothing is going to happen. And something only happens when this condition is triggered. So what we can do is we can try to fast forward the loop until that condition is met. And we do that with a kind of quantum linear search algorithm. So this is basically based on Grover's algorithm, where we search ever-increasing regions. And that leads to a quantum algorithm that will find the first marked element in a list in times square root of L if that marked element is at position L. So this works better than Grover's algorithm in general, where you would need to search over all possible values in the list. In this case, you're guaranteeing you find the first item in square root of the amount of time you would take to find it by linear search. But it is done just basically by calling Grover's algorithm recursively. Okay, so we're replacing this again with a special function. There's a final little bit of cleanup. And now we're at the point where we can identify the parts that need to be run on a quantum computer. So this find minimum function is now, as I say, it's based on that linear search algorithm. That part needs to be performed coherently. The function it calls also needs to be performed coherently. So we need to be able to compile these down to quantum circuits. But we're calling those as subroutines within a classical program. So this gives us a kind of systematic way of constructing a quantum algorithm to accelerate a particular piece of classical code in a completely procedural way. So that this isn't with manual intervention, this isn't a scientist sitting down trying to work out the algorithm. It's a system that's doing it automatically by just following a procedure. Okay, the last thing I wanted to show you just quickly is that we've started to implement many of these things in code. So the first 2 levels I showed you, the hydrogen and helium, we have built into an integrated development environment called Triple Alpha that we're just starting to open up at the moment. So you can program in these languages, you can compile them down to target different kinds of hardware. You can deploy them as quantum applications, but perhaps most importantly, for the context of this conference, you can do automated resource estimation or exact resource counts. So you can take a complex quantum program, you can compute exactly the number of each types of gates you need, even far beyond the limits of current systems. So we can do this up to trillions of gates, and we can get exact resource counts. So this is useful when it comes to estimating the requirements for fault-tolerant quantum computing and so on. Thanks very much.
Thank you, Joe. Questions?
I can ask a question. Or Robert. Yeah, this is very impressive, very interesting. Regarding energetic consumption, so I guess the obvious way software can impact the energy consumption is by optimizing the number of operations that is needed for the actual hardware, which you're doing. Do you see anything else than on the software side we have to pay attention to?
So I think there's two specific things to care about here. The first is what's important in understanding actual energy savings, if you want, is to understand exactly how much it costs to execute classically, how much energy you're going to use, versus quantum mechanically. So the broader an algorithmic advantage you have there, so the fewer operations you need. Okay, you do need to know some kind of energy cost per operation or however you want to break that down. But if you have that, then you can use these resource counts. It's not just about optimizing circuits, but the algorithmic advantage you get leads to a scaling advantage. So knowing the difference between a piece of classical code, being able to do a like-for-like comparison, saying this piece of code, if I execute it in one way, if I compile it, execute it in one way, what does it do? If I compile it to target quantum hardware, how does that work out? I think that's important because otherwise, like if you look at the variational techniques in QEI, VQE, all of these things, there's no classical comparison. You can say, okay, I'm going to compare to another optimization algorithm, but that other optimization algorithm will have different hard instances and different easy instances, and you won't be able to say, well, for this precise computation, which way does it go? Unless you try it. Whereas here, you're really replicating exactly the same code. You're getting the same input-output relationship as you would with the classical code, so it gets you into a regime where you can do like-for-like comparisons.
That's great. Any other question?
Yeah, so do I understand that this is really beautiful, I think, all of this automatic optimization, so you don't have to sit looking at circuits and try and think what to do, you just let a computer do it. But do I understand right now that all of your optimization is based on ideal gates? That you don't have you assume there's 100% probability that all of the gates succeed. You don't have a parameter that you can...
So this is more complicated because it's not a single level. So the way our system is organized, there's various different levels of abstraction, and it compiles through each of them. And you can say what happens at each one. The IDE I showed you and the compilers that are connected to that are only for the helium and hydrogen level, so they're not doing the classical code. That's still, we have it as a kind of tech demo, but we don't have it integrated into a product at the moment. We don't have it integrated into the IDE, so at the moment, it's like at the level you could write a paper. It's not at the level that you could start giving to understand. What I would say is, in terms of the optimization that happens, it happens at every level. Not all of it's fully in place at the moment. There's still work we're doing, for sure. But when you compile, for example, the C subroutines, okay, you saw the optimization in terms of just constructing a quantum algorithm. That's one type of optimization. The next is when you start constructing these classical subroutines, and I showed you gate counts. Those were just classical optimizations. So we're just optimizing the classical circuits first. And then we're using optimized constructions for the quantum building blocks that we use to implement those. So we're doing this level of quantum optimization on those classical circuits. Okay, so that's the next level of optimization. Then you get down to the level of, okay, I'm compiling down now to hardware or something like this, or I'm flattening my circuit. There's another layer of optimization that happens there. And we have two different optimizers we've been working on. One is a very simple one that uses kind of standard techniques. You'd expect the performance to be pretty similar to everyone else's. The other is gate set free one, so it works in a way where it like computes all of the different relationships between all of the different operations that have been potentially manually defined. So reads in your instruction set, generates all the possible relationships, and like crunches through that. So that's not fully integrated yet, but you can define noisy operations in that. So potentially you can map against a real description of what the hardware is doing because we allow for the description of Krauss operators. But that's not fully in place yet. And then the last level where this shows up is in the qubit routing. So in that, when we're doing the embedding into a circuit, again, we do it in a noise-aware way. So we do it by uploading a characterization of the processor, what couplings are good, what are the gate fidelities for couplings, what are they for single qubit gates, and so on, and working out the best embedding there. Now, is that canceling errors? Is it protecting against the noise? No. We've put a bunch of effort into getting to a point of being able to do automated characterization of the systems, so we can then start incorporating things like spin echo techniques to echo out a bunch of errors. We've been able to do this for a bunch of processors to multiplex the kind of measurements you would do to characterize coherent crosstalk within the processor. And we've some results kind of echoing out different subsets of these based on information about the couplings, but we haven't integrated it into the system yet. So that's still kind of ongoing work. So the answer is kind of partially, like we're, yeah, some stuff's in there, some stuff isn't yet.
How are we doing for time?
Okay.
I'd like to continue that discussion because I think it's really interesting, but I'll guess we're out of time, right? So we'll do that in private.
Yeah. Okay, let's move on to the next speaker, but let's first thank Joe for the wonderful talk.
Thanks.